Hi. So ideally, all of those engineering teams, manufacturing, design, automation, they're all in one org. They all report to one person. We can't point fingers at each other, so we have to solve them together, which is the best way to innovate. A traditional way of making a vehicle is this. If something goes wrong in final assembly, you block the whole line, and you end up with buffering in between. And when you watch it happen, it's actually really silly to a guy like me. You take all these stamp panels, you put them together, then you put them in a framing station, you build a body that looks something like a car, you put the doors on, and then you paint them. Once you get the color, you take the doors off, and then you start putting the interior inside the car. It comes in through the openings that already exist. I wish it went in like this big piece like this, but there's actually people coming in and out of the car. There's awkward movements. Then we lift the car up, we put stuff from underneath it, we put it down, then we put the seats in the car, and finally, we close it all out with glass, and we bring those doors that went away for a trip, and we put them back in the car. Most of the time, we're doing this with a big, giant car and moving it and doing really nothing to it at all. As part of the master plan, we have to make another step change in cost. We started this on Model Y when we made these huge gigacastings, and we deleted hundreds of parts. We simplified assembly with the Model Y structural battery, where we decided the floor should be a part of the car. The battery is the floor. We put the seats and the interior on the battery, and we bring it up through a big open hole, and we assemble it. And this allowed us to do things in parallel, fully rethinking the process and reducing the final assembly line by about 10%. And we thought, maybe we could do this other places. And what that means, it's going to look something like this, where we build all the sides of the cars independently. We only paint what we need to, and then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it, and it means we're doing more work on the car more of the time. And then, when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time. To increase the scale and adoption of electric vehicles on the orders of magnitude that we just showed you, it leads us to greater than 40% reduction in footprint, which means we can build factories faster, with less CapEx, more output per unit dollar. We'll reduce costs as much as 50%.
My name is Colin Campbell, and I have the real privilege of leading powertrain engineering here at Tesla. Now, the Model 3 and Y powertrain is a great example of this broader meaning of efficiency. So since we launched it back in 2017, we've continuously improved that powertrain and the factory that builds it. We did it by designing the entire vehicle and the entire factory together as one company, and this sets Tesla apart. We have small and highly capable teams, and to make a critical decision, we can have the battery cell chemists, the mechanical engineers, the manufacturing engineers, the supply chain team, the automation designers, the software programmers, all in one room, working together in real time. And that allows us to make decisions that are best for the whole car and to make them really fast. And that approach is unlike traditional automotive engineering, which is really fractured. Every electron that moves you down the road flows through one of these packages. We designed our own custom package, which is what you're seeing here, and we can extract twice as much heat out of that package as what we could buy off the shelf. The silicon carbide wafer that's inside those packages can be much smaller, and silicon carbide is an amazing semiconductor, but it's also expensive, and it's really hard to scale. We have developed our own custom microprocessor. It's purpose-built for high-power electronics. It's half the cost, and it does, in just one, the job of all of those four. And that expertise has allowed us to take the cost of the chargers that were in our Model S when we launched it in 2012, both the cost and the mass, and cut both of those in half. And even more important, the power electronics, they're central not just to our cars. They're also central to our superchargers and to our energy storage products. We've also done a lot of work in-house on software. So this is the drive unit, and they're responsible for just converting electricity into motion. And our custom software lets us simulate the rotating magnetic field that is responsible for that conversion. And getting that simulation exactly right, it's central to the cost, the weight, the size, and even the sound of the drive unit. And now, you can buy software that will do all of this, but our tools are faster, and they're more accurate, and that was not easy to do. And that allows us to quickly iterate through millions of possible drive unit designs to find the best one. When you are making a new product, it's not enough to think about the product itself. You have to think about how you're going to make it at scale. So at Tesla, our powertrain and our powertrain manufacturing equipment is both designed under one roof. The engineers who are designing the motor, they are in the same room as the engineers who are designing the machine that's going to put that motor together. And that collaboration pushes us from day one to design products that are not only high performance, but are really easy to assemble. In our next powertrain, so those silicon carbide transistors that I mentioned that are key component but expensive, we figured out a way to use 75% less without compromising the performance or the efficiency of the car. And of course, we know that battery cell supply is one of the constraints on the scalability of EVs right now. Our new powertrain is compatible with any battery chemistry. And that will give us great flexibility in battery sourcing. If we want to make EVs more accessible to people, they have to be cheaper. We've reduced the drive unit cost to about $1,000. And we don't think any other automaker is even close to that number. Finally, the bigger a factory is, the longer it takes to build. If we can build the same number of cars from a smaller factory, we are going to be able to scale EV production faster. Our next powertrain factory is 50% smaller than the one that's behind me today, even though it has the same capacity. As the world transitions to clean energy, the demand for rare earth is really increasing dramatically. And not only is it going to be a little hard to meet that demand, but mining that rare earth, it has environmental and health risks. So we want to do even better than this. We have designed our next drive unit, which uses a permanent magnet motor, to not use any rare earth materials at all. So how does all this fit into the master plan? We can make lower cost products that are still efficient and compelling, and we can make them at scale. We're going to use less of constrained commodities, silicon carbide, rare earths. We're going to build them all in compact and high output factories that are easy for us to build quickly. We're going to make that easy to scale powertrains all the way up to the levels that Drew and Elon mentioned at the beginning. So next, I'd like to welcome my colleagues Pete Bannon and David Lau.
Pictured here is the low voltage system of a Model S from 2012. This car was primarily designed with vendor source controllers integrated by Tesla. There are over 300 low voltage devices that encompass everything from the mundane, like the light in the glove box, to the complicated, like the infotainment computer, to the safety critical, like the airbags, steer-by-wire, and brake-by-wire. Going from S to 3, we reduced the wire harness by 17 kilograms. For the next-gen platform, we're going to finish the job and be designing 100% of the controllers, having full control of the supply chain at the component level. One of the changes that we're looking to make right now is to change something that's been steady for the last 60 years, 12 volts. The demand for power in the car has been steadily increasing to the point where we now have to have pretty large wires to drive over 200 amps of current around the car, which increases the mass and cost. We'll be moving to 48 volts. That allows for smaller wires, smaller E-fuses, and smaller controllers. It also allows us to make those heat sinks smaller, or in many cases, remove it completely, all benefiting the car in terms of mass and weight. It's one of the key things to enabling us to scale production of the low voltage systems for the Master Plan 3.
So I joined Tesla in 2012, and even in those very early days of the Model S, we already had the ability to update software over the air in all of the controllers throughout the entire vehicle, at a time when other cars were just starting to update software in only their infotainment units. And furthermore, we've had sophisticated, anonymized data logging and telemetry capabilities that allow us to understand how the fleet is doing, what customers are doing with it, and how it's responding in the field to that usage. These two capabilities combined give us the ability to iterate quickly on our software and to maximize the amount that we learn and proceed and the progress that we make in every one of those iterations.
Yeah, one example is that we were able to monitor and track the use of the sunroof in our cars and found that our customers never use their sunroof, so we made this easy decision to remove it.
As another example, We are able to use our collision data to design our crash safety systems for what happens in the real world, far beyond what regulatory and consumer ratings tests prescribe. And then furthermore, we're able to use that data to recreate in simulation all of those crashes every single time we make a change to the vehicle's design or to the software that controls the airbags and other restraint systems.
And last year, this data was used to change the algorithm for seatbelt tensioning to reduce injuries in the field, which was OTA to all of our cars.
We've analyzed patterns in the way the fleet drives and charges to optimally size battery packs for our next generations of vehicles. And this is extremely difficult from the way the rest of the traditional automotive supply chain is set up. In most situations, all the controllers in the car are delivered by different Tier 1 suppliers, whose software is written by Tier 2 suppliers, who farm some of that software out to different Tier 3 suppliers, and so on and so on. Making a change that spans multiple components takes months of coordination before any work can even start. And furthermore, integration of software in the server side with what's happening in our vehicles has always been a core part of our DNA and enables us to do things that nobody else can. For example, we recently released a feature in Model S and X that automatically, predictively adjusts and raises the suspension for ride comfort before the car hits a section of rough road. We do that by leveraging the fleet to generate a map of road roughness everywhere our cars drive. The restraint control module, whose inertial measurement unit senses the road roughness, the autopilot computer, whose GPS module and localizer figure out where the car is in the world, our navigation server, which aggregates the anonymized telemetry from the fleet and annotates our map with things like updated speed limits, lane topology, and now, road roughness. The onboard navigation engine, which looks ahead of the route that the car is traveling on and determines whether things are about to get rough. And finally, the air suspension controller, which takes all of those factors into account and decides continuously whether it is appropriate to adjust a suspension for ride comfort. And before we released this feature to the world, we sent prototype versions of it to the entire fleet that ran passively in the background, sending us anonymous data about every time it would have engaged, which taught us exactly how it was going to behave in the wild, in every environment, in every circumstance.
Yeah, being able to test new algorithms in the background without impacting the car is really critical ability for us, especially for safety critical things like automatic emergency braking.
How we leverage these capabilities in our own internal operations. So for example, when a production associate plugs something into the car, the central car computer sees that connection, confirms that it's the correct part for the type of car that's supposed to be built, installs a software update if necessary, checks configurations and calibrations, and runs a barrage of tests on that thing and all the other things that are connected to it. And if it finds an anomaly that can't be fixed purely with software, it throws an alert immediately that is displayed prominently on the vehicle's display, as well as sent to back-end command and control systems, so that a human can come over and fix the problem before the rest of the car gets built on top of it. And we're taking a similar approach in service through a combination of onboard vehicle diagnostics, natural language processing applied to customer narratives when a customer schedules a service appointment, and a suite of internally developed tools. We are successfully diagnosing, scheduling, and ordering parts for over 33% of customer concerns in service. You've heard at lots of other events about all the awesome things that our autopilot and AI teams are doing to make the car drive itself, bringing us into the future of autonomy. But we've also been thinking for years about all of the other pieces that we are going to need to manage a network of autonomous vehicles. Like in 2021, we built on top of our mobile app phone key and gave our customers the ability to share their car with anyone by sending them an invitation in a text message or an email. Last year, we introduced profile synchronization, which synchronizes your seat, steering, and mirror positions, as well as your settings, media favorites, and stored navigation locations across all vehicles in your account. Internally, we have an app that allows our personnel in engineering, manufacturing, delivery, and logistics to view, locate, and drive all Tesla-owned vehicles at their site. And when customers bring their car into service, when they receive a Tesla-owned service loaner vehicle, we are starting at some locations to automatically add that vehicle to the customer's mobile app account, so that combined with cloud-synchronized profiles and phone key, it's a completely seamless experience. As soon as the customer walks up to that loaner, it behaves and feels exactly like their own car.
Some of you might be wondering, hey, what does the self-driving got to do with the plan to a sustainable future? Currently, when the car is not being used, it is sitting idly in parking lots, not doing anything. But when autonomy is truly unlocked, this car, instead of being idle, can go serve other customers. This fundamentally reduces the need to scale manufacturing to extreme levels, because each car is being used way more. These neural networks take in the live feed from the car in real time of the 8 cameras in the car and produce a single unified 3D output space. The neural network-based planners are needed especially in complicated urban planning when there's a lot of other objects interacting with us. This would not be feasible using traditional compute. The second big piece of this puzzle is the data. This is where Tesla has a unique advantage because it can tap into the fleet to access the exact data that can fix the problems. Here, you are seeing a 3D reconstruction that is happening by collecting various clips from different cars in the fleet and assembling them, all of them together into a single unified representation of the world around the car. You can see all the lanes, the road boundaries, curb, crosswalks, even the text on the road being accurately reconstructed by these algorithms. Once we have this base reconstruction, we have a capable simulator that can synthesize adversarial weather, lighting conditions, and even the motion of other objects to test all the corner cases that might even be rare in the real world. Here's an example of why this data is critical and how we can solve problems using data. We had some false braking where we thought this car that's actually parked there was going to move into our path, and hence we were precautiously braking. What we did was we mined the fleet for similar cases where the car had false braking due to some parked car. We added 14,000 videos to our training set, and then once we trained the networks again with this new data, it now correctly understands that, okay, there is no driver in this car, hence it must be parked, so then there is no need to brake. And this is a systematic way to solve problems. On the chart on the right side, you can see that every time we add data, the performance improves. And then we can do this for every kind of task that we have in our system. The final critical piece is the compute. In order to train these large models in a reasonable amount of time, you need lots of compute. This is just compute in our data centers. In addition, we also have computers in the car which can run up to like 150 teraops of compute. All of this is going to significantly increase once we bring Dojo, which is our training computer, on board into this. We have already shipped our FSD beta software to roughly 400,000 customers who can turn it on anywhere, and then the car would attempt to drive to the destination. It's still supervised, but it can already handle turns, stop at traffic lights, yield with other objects, and generally get to the destination. We have observed that people who use FSD are already 5 to 6x safer than the US national average. As we improve the safety, the reliability, and the comfort of our system, we can then unlock driverless operations, which then makes the car be used way more than what it is used right now.
The thing that I think Tesla brings to the table that others don't have is that we're the most advanced in real-world AI. So the same AI that drives the car, which you can think of the car really as a robot on wheels, and this is a robot on legs. And so the same team that designed the groundbreaking electric motors that are in, say, the Model S Plaid, designed the actuators in the robot. We should be able to bring an actual product to market at scale that is useful far faster than anyone else. And assuming that the things I'm saying are true, it's just a question of the timing. So you could sort of see a home use for robots, certainly industrial uses for robots, humanoid robots. It's not even clear what an economy means at that point. Since an economy is output per person times persons, but if output is much higher and there's no limit on persons, then what's the actual limit on the economy? It's probably the least understood or appreciated part of what we're doing at Tesla, but will probably be worth significantly more than the the car side of things long term.
Hi there. At Tesla Charging, we have understood since day one that a great charging experience is the linchpin to electric vehicle adoption. We've spent 10 years building charging infrastructure when basically no one else in the industry would do it. So we have the industry's lowest deployment cost. We're vertically integrated. We manufacture and engineer all of our own charging equipment. We share components across our different product lines. And Trip Planner is our in-vehicle routing or navigation system. Other electric vehicle manufacturers, well, some of them have vehicle-side data. Other infrastructure providers have site data. But at Tesla, we have both. And what that allows us to do is to use Trip Planner to route vehicles towards available sites and away from congested sites so we can balance our utilization without risking wait time. And the results speak for themselves. Over the last few years, we've been able to drive up site utilization by 30%. That means lower per kilowatt hour cost, while also cutting our wait time in half. And we think this can get even better. Today, we're feeding Trip Planner with real-time site information and information about vehicles currently at sites. Going forward, we'll be moving that to projecting site occupancy based on the understanding of what vehicles are currently routing to those sites. And ultimately, our vision for Trip Planner is that it's the air traffic controller for electric vehicle charging across all infrastructure on a global basis. We've shaved off 30% of our charge time, average supercharging site time, visit time, over the last few years. This has taken improvements on the hardware side, with our software, on our vehicles, and on our infrastructure, and we're really excited to continue pushing this trend down. As we look forward and we talk about this fully electrified fleet on a global basis, we really want to make sure that the demand for charging more closely follows when renewable sources are available. We want to kind of move that charging curve, and for solar and wind in this example, it means more daytime charging. And we think the best way to go towards daytime charging is to install AC charging that is convenient and low cost everywhere vehicles are typically parked throughout the day. So that's really the plan. While supercharging and home charging definitely stay a big part of the puzzle, our teams are currently scaling to install AC charging everywhere vehicles charge during the day so we can power them from renewable sources.
Thanks, Rebecca. The level of detail that our engineers get involved in terms of building the capability of the suppliers is pretty detailed. So, once we get a new part, naturally with electric vehicles, a lot of the supply chain doesn't exist. Our engineers would basically take the drawing, turn it into a manufacturing concept, do the equipment selection, and physically go to the supplier and stay there for weeks or months, however long it takes, to basically do the line bring up. Once the line is brought up and we're hitting the right rate, the right quality, at the right yield, then we work on things like automation and yield improvement and those types of activities. Now, this is a huge strategic advantage because we manage every detail of our supply chain, because we're so integrated with our partners that we know about issues before they happen. It's almost live. We've got dashboards, we've got connections, and across the 10,000 or so factories across the world that are making our components, we have a pretty good view of the health of those suppliers. For example, if you're talking about the battery cell, we really get involved with the mines of like where we're procuring the lithium, the cobalt, and all that sort of stuff because we're procuring such high volumes of it. So you'll see a reduction in the number of parts on the SNX platform to the 3-in-Y platform. And this is because of the great work our design engineers have done of making the car simpler and easier to manufacture. In parallel, we actually had a similar strategy in supply chain. We've really dramatically reduced the number of suppliers that we were dealing with for the 3-in-Y platform. And this is an approach we'll continue to do for future platforms as they come along that are even more high volume. Meet the car computer. Very innocent sounding name, and it's anything but. This is an absolute monster to manage. We started focusing on making this more efficient. The only way to control cost is by removing labor. The first step is removing labor. The second step is fully automating. The third step is turning off the lights and letting the factory run, ideally.
Fully automated is the only way to go. Before we automate the line, we created a 3D simulation. Now, not many companies or teams have this capability and tell the suppliers exactly what equipment to purchase, what to test, and create an end-to-end line in simulation. We implemented this fully automated line in less than 8 months. A line that would need 1,000 associates now just takes 10 associates. And the quality also went up by an order of magnitude. In a world where labor costs are increasing, labor participation is decreasing, there is a huge turnover, and the cost of implementing automation is going down by 3x in the next 10 years. This is the only way we think we can confidently scale to the 20 million vehicles.
Hi, everyone. My name is Tom Zhu. So right now, we have 4 vehicle factories on 3 continents to serve our markets. The total number of manufacturing employees is over 65,000. The total installed capacity in all these vehicle factories about 2 million cars a year. That said, we're always looking for opportunity to grow more capacity from the existing footprint. So you expect this number will grow over time. People always ask me, how Tesla can build a factory that fast. We have a very strong in-house construction team in Tesla. So this team didn't just build Giga Shanghai, they also built Giga Berlin, Giga Texas, and Giga Nevada. Going forward with the new platform, the more modular design and densified Gigafactory, we'll be able to make more cars from even reduce the footprint. That also means we can build more factories at the same time.
Yeah, we're not just talking about new vehicle factories, but also new cell factories. We've reduced the number of parts in the cell, the number of processes, significant reduction in the number of processes, and collaborating with those 5 design groups, we've been able to end up with a factory that's 10 times smaller volumetrically, which means it's faster to get built, it's much lower capex per gigawatt hour output, and we can go and scale to our objectives of 240 total terawatt hours, 1 terawatt hour a year of stationary storage and 20 million vehicles a year. And we're not just looking at the cell factory itself, but also upstream materials where necessary. What you see here is the rendering of the 50 gigawatt hour a year Corpus Christi lithium refinery that we've already broken ground on here in Texas. The facility will start commissioning by the end of 2023. So we are doing this where we need to. Our plan is not to do it always. There are lots of competent companies out there. But we are also trying to sort of accelerate the pace of the industry by trying some new things that are a little bit more scalable and de-risking certain innovations that improve productivity in terms of capex per gigawatt hour and things like that.
Hello, everyone. My name is Mike Snyder. I lead our Megapack organization. We're on our 6th generation of our industrial product, which is the Megapack XL that we're building out of Lathrop, California. We've deployed over 16 gigawatt hours of industrial and residential products across 50 countries. And really, Megapack is a market leader. It's best in class in efficiency, reliability, energy density, and easiest to install, lowest cost to install. What we end up with is the most energy-dense solution on the market, upwards of 300 megawatt hours per acre. And just as a frame of reference, this solution is 2 times more power dense than a typical gas peaker plant.
This is the product that retires the fossil fuels.
Yep.
1 power plant at a time.
Tesla is a leader in power electronics, and we deliver more power electronics than the solar and the wind industry combined on a per annum basis.
And power electronics, they are really the glue in the sustainable energy economy between generation, storage, and the end use. Those power electronics devices are switching thousands of times per second, hundreds of thousands of times per second to efficiently react to whatever is needed, either in the car or in the grid. And because they are so sort of software driven at their core, they can provide functionality that hasn't been available to the grid in the past.
We have a firmware feature that we call virtual machine mode. It contributes to grid stability like a car's shock absorber. So you can imagine if you don't dampen those vibrations, the vehicle could lose control. On the grid, you could have a blackout. We have one grid operator that's utilizing virtual machine mode and said they will not operate their grid at 100% renewables unless they have this feature, unless they have virtual machine mode working. I believe it's the future of how batteries are going to add value. It's going to be more about adding power stability just as it is about energy. AutoBidder is another software feature I wanted to mention. AutoBidder is an autonomous energy trading platform that in its most basic sense is buying energy low and selling it high, and the owner can net the difference of that. Second point of how we got here, a relentless focus on speed of execution, and there's 2 points to be made here. First one is in building factories. Second, it's about installing projects faster. I've mentioned this already, but plug and play is kind of at the core of what we're going for. Over the past 4 years, we've increased the installation speed by 4x, and we've reduced the total labor involved across both construction and manufacturing by 3x. We think that this is key to unlocking our ability to scale and our customers' ability to scale with us. We need to be laser focused on reducing that time from when the Megapack leaves the factory to when it is operational on the grid.
And it's not just about centralized storage, it's also about distributed storage. Tesla Electric really unlocks the full value of distributed energy and storage products. It enables our customers to become their own utility. The data on the page is from our South Australia virtual power plant. Over 2022, it's 5,000 customers that we have the data for. You can get a sense for what's happening. So just if they were being provided default utility service and you looked at the cost of serving them that electricity, on average, $140 a month. If they all had solar and Powerwall, but the solar and Powerwall wasn't interacting with the grid, wasn't participating in the energy market, the cost of serving that customer would go from $140 a month to $70 a month. If Tesla Electric is operating those assets in an intelligent way to benefit the grid, Tesla Electric being basically a software that we developed out of AutoBidder for the purposes of these distributed energy resources, we can actually pay the customers to bring their energy services to the grid. That's what happened in Australia last year. This is an indication of where this is all headed, of both centralized and distributed storage resources providing the key to unlocking fully renewable grids. Here in Texas, by this summer, we're going to offer a retail electricity plan to people who have our cars where they can have unlimited overnight home charging for $30 a month. And the reason why we can do this is because Texas has a ton of wind. And in Texas, the wind blows at night. So actually serving these customers with electricity at night for their cars is the best thing to do for everyone. And so this is a way to incentivize people to charge at home at night directly from renewable power. It's part of the grand master plan we talked about at the beginning. We're really at the beginning of this massive ramp in energy storage deployment.
Hi, I'm Brandon with the legal team. Thank you.
Anyone at any time can raise an idea or make an improvement suggestion. And as take charges go up, as you can see in this graph, injuries go down. And you know why? People who do the work. The people who do the work know how to improve the work. Sustainability is everything. It's our mission. You've heard about it all day, part of our master plan. But at Tesla, we don't just tick boxes to meet a requirement. We really focus on the impact. In 2021, our customers avoided equivalent to taking 1.7 million ICE vehicles off the road for a full year. We have year-over-year reduction in our water use, in our waste. From 2012 to 2021, our products generated more energy that was consumed by all Tesla vehicles and our factories. Even in the worst case scenario, 100% coal grid, the Model 3 has less emissions than the average ICE car.
So this is our last section of our prepared remarks today. If we look at our longest running scale production product, this is the Model 3. We reached 5,000 cars per week, which was our design capacity in mid-2018. And since then, we've taken 30% of cost out of this product. And there's 2 points I want to make about this. The first is that cost reduction, as you have heard throughout the course of the day, is deeply ingrained in our culture, and I think one of the most important reasons why we are here today as a company. The second point that I want to make is that when we're working on cost reduction, it's easy just to take cost out and make our products worse. But we have to take cost out and improve our products at the same time. This is the hard thing to do, but it's the necessary thing to do to continue to move forward. And if you look at a version of a Model 3 that we built today, and you compare it back to a Model 3 that we built in 2018, there's a long list of improvements that we put into the car while also taking cost out of the product. And as we look forward to our next-gen vehicle, our target is to reduce 50% of cost, and we've talked about that a bit earlier today. From going from the Model S and X platform to the 3 and Y platform, we took out 50% of cost, so the task here is to do it again. And this is very important because as we improve affordability, the number of customers who have access to our products dramatically increases. And as we link this back to our master plan, it enables an exponential growth in our volume with linear reductions in the cost of our products. The second point I'll make here is that, and again, cost reductions don't come from any single one place. And so you can see the buckets here on the vehicle side, battery and powertrain, manufacturing cost reductions, and others. These buckets are relatively equal in size. And so in order to take 50% of the cost out of the product, we have to go through everything. This chart here is showing what the total cost of ownership per mile is over the course of 5 years. And we have to think about financing costs, insurance costs, the cost of power, wear and tear and maintenance on the cars, et cetera. And we're already at a place today in the US where a base Model 3 on a cost per mile basis is less than a Toyota Corolla, which is the highest selling car in the world. And as we move towards our next-gen platform, we will continue to reduce this. And as we work on robotaxi variants of this platform, this cost will come down even further. The next thing on cost reduction I want to talk about is operating expenses. The first component of OpEx, which is R&D, the single most important thing here is that we constrain the number of programs that we work on, so minimizing the number of programs that we're running in parallel. And the key here is to maximize the revenue and cash generated from every program that we work on, and also maximize the technology sharing between the programs. So we talked a little bit about how power electronics in our energy business is shared with power electronics in our vehicle business. So we're showing here a comparison of SG&A per car delivered compared to the traditional auto industry, which is both an OEM and the dealership network. And our estimates are that we're 60 to 70% lower on a per car basis. And if you turn this into dollars, this is many thousands of dollars per car. It's 7,000 cars a week, 350,000 cars a year. We want to go to 20 million cars a year, and we're struggling at 7,000. And we're saying to ourselves, we have to completely rethink the way that we're managing our back office operations if we have any hope of efficiently scaling this company. And so this began a process that we're still continuing to work on today, but it's something that we refer to as the Tesla operating system. So in the same way that we're vertically integrated into the software that manages our cars, we've also vertically integrated into the software that runs our company. And all of our major departments in the company are using, not all of them yet, but almost all of them are using our in-house software. And this matters a lot because rather than having a complex web of third-party systems that are generic solutions that take a lot of effort to customize for our particular needs, we've been able to put in place with an in-house applications engineering team dedicated, lightweight software that does only what we need it to do and nothing more. And that team works very closely with process improvement teams that sit within the business, who are looking through all of the processes that we're managing as a company and following the exact same process that Tom mentioned in the manufacturing space to look at our processes, delete process steps that we don't need, simplify process steps that are existing, and automate what's remaining. And the results of this have been quite staggering, to be frank. I think it's exceeded our expectations as well. On the left side of this chart are some examples of the efficiency improvements that we've seen within our SG&A areas as a result of this strategy. The North American sales team is 4 times more efficient now than they were in 2018. Order operations team, financial services, I mean, these levels of improvement are large, and there's not enough pixels on the slide here to list out everything, so it's just a couple of examples. And then in the same way that when we look to take cost out of our products, we want to feature up the product or improve the product while taking cost out, the same has been true with the use of Tesla operating system and that integration with our process improvement teams within the company. And so we've increased performance and added capabilities while also dramatically reducing cost on a per car basis. There's a list of self-service functionality that we've put in place, which customers like. It also simplifies our operations behind the scenes. We've used the Tesla operating system to expand into our captive insurance space, which we are fully vertically integrated into. We run our own in-house software. We have our own agents, our own claims software, and claims folks who run our insurance business. This is also very important because as a technology company, data is very important. And we use these systems and the access to the data in those systems to pull out extremely granular and targeted reporting that enables us to see every aspect of our business in real time so we can make adjustments to our operations as needed. And there are sometimes examples where we say, man, I wish we were tracking this piece of data. Well, it's a Teams meeting away from the applications engineering team to make a request, and then we can start tracking that data and make those changes. And so the feedback loop associated with process improvement inside the company is pretty astounding. So all of this work on cost reduction is extremely important because we have a lot of money to spend ahead of us to achieve our goals within the master plan. So we've mentioned over the course of the day today 20 million annual vehicle production as our target, 1 terawatt hour of annual energy storage production, and then expanding cell production, service, and charging in line with the growth of those other businesses. And so we've estimated what we think the total cost to get there will be, and there's certainly error bars around these numbers as we continue to progress and innovate. But of this, we've spent about $28 billion of that so far in the history of the company. And if you look at our 2022 operating cash flows and you just say, well, let's assume some modest growth to that, maybe not all that much, the ability to pay for this level of investment from the forecast that we have is very achievable for us. A couple of key messages I just want to leave you all with here is that we use innovation at an intense level to drive costs down and improve the efficiency of the business. And the reason this is so important is it allows us to improve product affordability. And this is particularly the case when we move to our next generation platform. Improving affordability allows us to comfortably make investments that grow volume. That volume generates cash that then allows us to make more investments. And as we integrate that going forward, it's our belief as a leadership team here at Tesla that we're going to achieve unprecedented scale in the manufacturing space. And this is what's ultimately required to accelerate the world's transition to sustainable energy.